Hello, everyone. My name is Mads Barami from Wolfram Research. I would like to welcome you to the second session of our live coding series with Andreas Lauschke. Andreas has a master's degree in financial mathematics from Technical University of Berlin, and he has been using Wolfram technology for more than 25 years. During his live coding sessions, Andreas will live demo key features of Wolfram language that are very useful in data science and beyond. I should mention that he will talk about lots of things beyond only data science. For the first session, Andreas focused on the operator notation and application. You can find the recorded video on Wolfram YouTube channel. Andreas has also uploaded his notebooks together with some homeworks for you guys on Wolfram Community. Please go there and submit your answers. Today's live coding session is about association and dataset. Without further ado, let us welcome our instructor, Andreas Lauschke.
Yes, thank you, Matt. Hello, everybody. Good evening. I'm in the Eastern time zone in the United States. Good evening. So today I will introduce the associations and the data set, and I am making this part one. There is so much to be said about them that I will also give a second session about this. I think associations and data set go hand in hand, and I think the funnest way to introduce associations is through the data set. The data set needs the associations. It's based on associations. But the associations go far beyond usefulness in the data set. They have a lot of value on their own. So I will introduce them together in two sessions, but bring them together, associations and data set. Before I begin, though, I would like to make a comment about a comment that I got last time, 9 days ago. There was a very intelligent comment from Rohit, and I would like to address that. Rohit posted that we can mimic, at least mimic, the operator notation with a pure function. And that is certainly true, right? It is not an operator notation in the sense that it is meant in the Mathematica system, but we can certainly use pure functions to mimic them. You can use pure functions and currying in order to get the operator notation. So a little modification of what Wolf posted was the part with a pure function, and yeah, certainly it works, right? We start with 50 and I want to pick the first 20. So using part here definitely mimics it. And I also talked a bit about take and drop last time, because they're not in the list of functions that have an operator notation, although I think there should be, and I believe we probably get them in the future. And we can do the same thing here, right? We can use pure functions. You see the green hash and then the ampersand at the end of it. So it clearly works. You can always mimic it that way. But a real operator notation wouldn't need this, right? As I've shown you with several examples, this extract workaround for take does not use the pure functions. And sometimes the pure functions are the only way to do postfix. If you're forcing yourself to use postfix, then sometimes they're the only way to do that. But it's not always straightforward or simple. The simplest way to invert a vector is, of course, to use the listable attribute. But you can certainly apply 1 over hash in postfix, right? It certainly works, and you can certainly do that. It is the only way to do some postfix that you want to do. All right, so as I said, postfix and operator notation can complicate things, and it's not a holy grail, but they can be very useful if they are used properly. All right, so then let me jump into the session for today. Start with the associations, and I'll start with the motivation here as well. The motivation for an association is to have a data structure in the kernel that is similar to what in other programming languages would be called associative arrays, dictionaries, hashes, or maps in other languages, right? There's map as a function and there's map as a data structure. And here I mean map as a data structure. And they work as you would use them in a dictionary. You look up an entry based on a keyword, right? That's how you use a dictionary. That's why in some programming languages it's called a dictionary. And in Perl, for example, there would be called associative arrays. First you find the keyword, and then you can read the entry associated with that keyword. So it associates a key with a value. All right, here are some of the basics of the associations. They are a set of bindings between keys and values. They are very efficient for looking up the value given the key, and they are designed in the kernel for several millions of elements. Very efficient lookups, a very efficient creation. So this is meant for data science. This is meant for industrial strength applications. You can quickly go through several million of elements. The keys and the values can be arbitrary expressions. You can use strings, you can use numbers, you can use any valid expression. There's practically no limit, right? And we will look at a couple of examples where we have more involved expressions for keys and values. The entries and associations are ordered, and associations are very convenient in creating hierarchical structures, and that's what I will demo during the next session. So we use a bracket and a pipe operator at the beginning and at the end, and then we just use rules inside to set up the keys and values. So in this case, 1 goes to 33, 2 goes to a symbol that's called ANTR. You see it's blue, so it's not evaluated yet. 5 goes to itself, A goes to B. Here we have a string that goes to a string. Here we have something that's not evaluated yet, and as a key. Here we have another string going to a string. Here we have a difference going to another difference, and here we have a key going to a plot. So let's evaluate them. And the lookup is very simple. You use the symbol that you have. In this case, I have assigned it to a symbol called a sock, and you just look them up. So for 3, we get pi over 2. That was here in the list. For 7 squared, we get 7 squared, which was hello. But we can also pre-evaluate it. SOC of 49 is the same hello. And SOC of 4, that takes the 4th element. If we take this part notation, then it's the 4th element, not the key. This 3 here is in simple brackets. So we're using the key, and note that this is not in the 4th position. But here we are using part 4, so now it's the 4th expression. So 1, 2, 3, 4, and the value here is B. This is the B here that you see. They can be turned into lists with normal, and you now see basically the same thing, but as a list. So there's an equivalent between lists and associations, right? You see those curly braces here. Note that this is now a list, right? Same representation. It's very useful, for example, to visualize the association structure. So let's do a tree plot. And we see that we have A was going to B, another one where B was going to C, and C was going to D. So keys can point to values, but the values themselves can be keys again to other values. That's why here you see A goes to B, goes to C, goes to D in the first one. The 5 was pointing to itself. Here you have keys and values where the values are not keys again. It's very good to model structure hierarchies, like Frankfurt is in Hessen and Hessen is in Germany. And here we have a plot goes to this plot. This is now the label of the vertex. So it's very cool to visualize this with other functions. You can never get lost in this, right? If you have a complex association, then you can always look at the tree plot. Okay, the tree plot then can also get too complicated, but as long as you can plot it, you can understand what you have defined. The lookup tables and key value structures are really nothing new conceptually. They have existed all the time. And this is like a typical associative array in Perl. We can say the mortgage of Kathy is 1765.23, and so on and so on. We can use strings on the right side. We can use integers. We can use anything, plots, whatever we have there. But there is a critical difference what makes the association much more useful in many cases. With them, we got the associations and they have focus on performance, but they also provide a certain context to the surrounding function. When you give it a list, well, that's one thing, but when you give it an association, the surrounding function notices now that it is an association. So when we here have days of November, then November is not evaluated yet. You see it's blue. We just get the 30 back that we had defined here, right? It's this. But when we say days of, and now we assign this to an association, we have a one element association. And if you look at the full form, we see that here, association of a rule, which is quite different from just the 30, from just the number. This is just an integer. And here the fact that we're not just talking about a binding of a key to an array, but we have a thing association that makes it possible for surrounding function to get some context. For example, you can list plot association, and that will give you a legend automatically, like this. You see that it didn't have to specify that I want to have a legend. The list plot does it automatically because it knows it is an association. And we have integers on the right-hand side, that means the values. So we automatically get a legend. And that was possible for list plot to do because it discovered that its argument is an association. For that to work, list plot needed to detect that an association was provided. And we see more of that when we look at the dataset. So how do we construct it? You can use the association symbol, and sometimes that's easier programmatically, or you enter them directly. Right? You can say association brackets, and now you define your key value pairs, or you use the bracket notation, whatever is better for your code. When we look at G, then we see it's a global symbol called G, and the assignment is this association. All right, very important functions are association thread and association map. The association thread allows you to create associations when you have keys and values in separate lists. They can come as two lists. Note that this is a key list and a values list, right? So here's a list and here's a list. So the first list are the keys, the second list are the values. We can also make it as a list pointing to another list, right? If we evaluate this, we get 1 goes to 1, 2 goes to 2, 3 goes to 3. So they can be lists with a comma, they can be lists with an arrow. So this allows you to create associations easily just by giving it keys list and the values list. Here's another one, right? Here we have 100 elements, and here we have 100 elements. So they will match, and we can simply use association thread, very code efficient to create these associations. Association map is also an extremely powerful way to combine function application with the creation of the association. It applies a function to a list of elements that are assumed to be keys of the new association. And from the help browser, fairly clear, right? We say F, and then comes a list of the keys. So it creates the association key 1 goes to function of key 1, key 2 goes to function of key 2, and so forth. So very simple example, my function is string length, and I send it over a bunch of animals. That gives me the string length of these strings of animals, and you get them back as an association. It can be symbolic. Notice that foo is blue. Oh, that even rhymes. And you now get an association where you have the values as the keys, and I'm sorry, the keys as the second argument, and the values are now the symbolic function foo applied to their respective keys. You can use pure functions, my favorite type of function, right? You can use pure functions. Again, these are the keys with association map. the keys are the second argument, an association thread there, the first argument, and you're applying this function over these keys, square them, or divide by the cube, or some binomials, or plot, or whatever it is, right? It doesn't matter. So then you get these associations back where you have a key pointing to the result. And note that these are associations, not a list, right? It's 1 goes to something. 6 goes to something. Yeah, notice that this is not a list of plot, it's an association, and the plots are the values, the integers are the keys. So let's plot different tangent functions here. You see that these are associations and not lists. Reverses the rules of keys and values. So for example, we start with A goes to 1, B goes to 2, and we get back 1 goes to A, 2 goes to B. And you can operate on the values directly. Sometimes you need to operate just on the values, do nothing to the keys. That leaves the keys unchanged. Association map applies the keys, first argument to the second argument, but you can also use simply map. Why shouldn't you be allowed to use map on associations? So here we say we want to square the values, we want to leave the keys unchanged, right? Then we get this. Or let's total the lists that are in the values, right? You get A1 plus A2, B1 plus B2, and so forth. We can use pretty much anything, pretty much any function and any data that are compatible. So here we have an association where the values are 2 by 2 matrices. Now, what can we do with 2 by 2 matrices? Or square matrices in general, we can compute the determinant. So here you see the determinants of these 3 values as values. We obviously need a simple way to get a list of the keys and the values. Would be foolish if we couldn't have that. So we just use keys and values, right? We just supply the association to the keys symbol and to the value symbol. So here we get them back. Okay, a typical use of associations, if not the most prominent one, is to set up the association in a way that the keys have an interpretation of row and column, right, as a table or spreadsheet would have. It's a fairly typical use of a two-dimensional table. There is meaning in the rows and there's meaning in the columns. For that, you set up a list of associations so that the rows are the associations and the keys are the column labels. For example, let's take this. Notice that this is a list of associations. This is important, right? The associations themselves are the rows in that list, right? You see that this is not an association. The outer one is a list. And this is how we're getting this here. Let's look at the input form and the full form, right? Those are your best friends if you ever need to know what the expression is and how the kernel interprets them. If you make mistakes, then, well, the kernel doesn't know this. So input form and full form are your friends. You can always look up how the kernel understands the expression you gave it. Yeah, sometimes the tab view is a very space-saving way to look up multiple nested structures. All right, and in this form, we are ready for the next section, the dataset. And as a list of associations, where every association represents a row and every key represents a column, we can start the dataset. So let's look at my table. And you see that we are already getting a table where we have column labels, the name column, the age column, and the sex column. So now show I browser section? Yes. So let's do that. I want to show you something here. You should look this up for yourself. You should, where is my head browser? Here. Go to details. Here, I want you to look at this section, right? If you give it a list of lists, you don't get labels. It's a table without named rows and columns. A table with named columns, that's a list of associations. That's what I just showed you. You can also use row labels. Then you would specify it as an association of lists. And if you give an association of associations, you get row and column labels. All right. But here we just have a list of associations, so we only get column labels. And a big thing about the dataset is its interactivity. You can click on the labels and drill in on detail. So for example, if I click on name, I get Bob, Bill, and Stacy. And if you go here on this spreadsheet-like symbol, then you get the full association back. This is extremely useful when you don't just have 3 by 3, but you have hundreds of thousands of rows and columns. Then it's very good to drill in interactively. All right, very, very useful. All right, the data set. It's seriously cool stuff. It's a concise query syntax for powerful transformations. It's shorter and faster than SQL queries. Sometimes raw data can be very unwieldy to work with. It can be too large to display. The nested structure can be difficult to discern. It's hard to write complex analyses and transformations of the data. It can be hard to debug or trace. And if something goes wrong, it's hard to find out why. And the data sets solve these problems. You can display large data in a convenient format. It displays nested structures in an intelligent way. So for example, you get automatic column headers, number of nesting levels, and the total number of elements formatted left-aligned. And it comes, if it's a lot of data in it, it comes with scroll bars. So you can jump to first, you can jump to last page, you get an automatic grid frame. So it's typically used to manage objects that have the same properties, like columns, right? Column labels. So this is like rows and columns on the table. And we can keep the nesting in these lists. And in the next session, I'll show you the moons example, the moons and the planets. That is, I think, an extremely useful example because every moon has a different number. I'm sorry, every planet has a different number of moons. So we go to that next session when we get into nested structures. So it allows for easy mapping and selecting. And you can easily extract individual rows and columns to get single records. I have to speak out a big caveat. Many people find the dataset confusing. And in the past, I got verbiage such as not intuitive, or it's hairy, or I never use it except for visualization. I prefer a list of associations of associations of associations. With all these operators, I get confused. And there's something to it. You have to get familiar with the data set and with the notation. It can be a little bit daunting at the beginning, but I still recommend you get familiar with it. It is definitely worth the effort. I will admit it takes some getting used to and some experimentation to harness its full power. So I'd like to use the Titanic example. It's, I think, an example that is sufficiently powerful to explain the data set, but sufficiently simple to keep things on an introductory level. So we just load it with example data, and we understand from the normal form, there's a column class, one is age, one is sex, and one is survived. And note the format, it's important to understand this. This is a one-dimensional list of several associations in which every element has a column label and as a key and a value corresponding to that key. That's like rows and columns. Let's look at the full form. And here we say the outer symbol is a data set, and then we get the list of these associations. All right, so if we display the data set directly, we already get it nicely formatted in the data set. And I found it particularly useful that we now can scroll forward, like page-wise, and we can jump to the end of it, right? We can jump to the last entry. See, this says showing 1290 through 1309. Imagine you have a big spreadsheet. You have to scroll the whole screen, right? And here you have something that is scrollable within your front-end session, right? You don't have to scroll the whole notebook. you can have this data set that doesn't take too much space on your page and scroll inside the data set. So now we have to talk a little bit about queries. And the way I think it is the easiest to understand the data set is right to left. And I know that may be unintuitive for some people. We first start out with the class, and then we're asking how many were there per class. This is right to left, right? We are more asking for the counts in every class. You don't have to do it that way. You can go left to right, but then you need to use prefix again, right? You can skip whenever you can say all, I think, and it's avoidable. I would like to leave it out, but you would need to say all here if you want to enforce left to right. But now we need prefix notation. This is prefix notation, right? We have the counts is now the argument to this operator. You get the same result. And if you prefer left to right, by all means, do it this way. I personally prefer to go right to left in a data set. How many men, how many women, right? We can now use it to query on sex. It's the same as above, we're just using a different color. So we find there were 466 women and 843 men on that boat. How many survived and died? Well, now we're asking for survival status. Again, I give you both forms, right to left or the longer left to right form. So 500 survived, 809 died. Let's do the next column. There was age. And you see that sometimes data is missing. You see this ... here, 263. So that's also very pervasively implemented in the mathematical system, that you can simply say underscore missing, and that goes through all these queries, right? It propagates forth. We can find out that for 263 people, we don't know the age. Very nicely done. And here's where we have, we can use right to left, left to right. And I will show you a couple of these formats just to present you with these ideas. You have to decide which one you like best, which one you like most. So, yes, I will show you a couple of these alternatives so you can pick and choose whichever you prefer. And there are several ways to do this. You can, of course, use regular postfix, but n is not an operator. This would be an operator. And here, of course, this is, of course, an operator. And note that the data, I didn't give it any data. The data is included in Titanic. This data set already contains the data. So all I needed to do here then was use operators, right? This is, as I've shown last time, this is composition. And it binds right to left as well. So in the last example, look that we had mean of n as an argument to the data set, and I use parens to demonstrate the order here, right? This does not bind as left to right, and I've set these parentheses to explain my point. This doesn't work. This leaves it as this Titanic object, and then we ask for mean. We get something, but then this operator here cannot do anything with it anymore. So keep in mind how this binds. First, we evaluate this, and then we apply it to Titanic all age. Right? So this can be tricky, and that's why I'm saying don't get too dogmatic on left to right. It's really sometimes better right to left, due to the higher precedence of a composition over this apply in the presence table. So indeed, perhaps a bit tricky because you need to evaluate this first. Well, here I'm just writing down what I've just said. You get it in the notebook. So the interpretation is also much easier that way if you go right to left, right? Here you read it as take the mean of the ages and then turn it into a real. If you do it differently, then it gets more complicated. Start with the ages and take the mean of them and then turn that into a real, whichever you prefer. All right, the min, the mean, and the max. If you want multiple functions applied, then just use braces. So we have that here. Here we get the min, the mean, and the max. That is this row here. So whenever the evaluation of the query turns out to be one number, you just get that number. You don't get a data set of that one number. So the min is just this number. The mean, if we just query that, we get this fraction here. This is a rational. And the max also will be one number. But if we do this in a data set, then it automatically rounds, because this fraction would be a little bit too big, a little bit too bloated in this row. So here you automatically get the application of n, because this is supposed to be a decimal now. All right. So you see that rationals in the data set are automatically turned into reals when the fraction gets too tall for display purposes. We have very robust error handling. For example, if we query for nationality, well, the system tells us, look, that's not a column, and that's not a column in the data set. We don't have nationality as a column there. And now the sky is the limit as to the query or computation or visualization that we can use. For example, on an H column, we can apply a histogram, right? We instantly get a histogram of this. Extremely code efficient, right? I can't get over it. Try to do this in one of those traditional languages, and it's going to take you forever with a bunch of code writing. And I want to tell the system what I want to see, not how it's supposed to be done. So in these examples, you've noticed the pattern. The operation was always an operation that works on a one-dimensional list. That's because we specified H in the second argument, which is a column in the underlying. So again, think of right to left. It makes things much easier. So this way, then I can simply say, give me the total of all the ages. Keep in mind that 263 people, for them, we don't know the age. So that brings me to the question, are there some ages missing other than missing ages? So we know that some are missing, but we also know the youngest person was 1 year old, the oldest person was 80 years old. Brings up the question, is there something missing? Are there maybe ages for which we didn't have a passenger? So the function to use for that would be complement, right? I'm setting up a list of 80 integers, 1 through 80, and I'm asking, well, is there something maybe that's missing? So these ages didn't have a passenger unless some of those missing age passengers fall into these what is it, into these 8 ages. Let's add another layer. Again, think right to left. We start with the class, then for every class we count how many fall into that class, and then we group by sex as the grouping key. And this is the leftmost argument. This is important. And when you do a grouping as the leftmost argument in the data set, these will be the row labels. You see that I group by sex, and that's why my row labels are female and male. Those are the row labels for what's coming to the right of it. We can also group by survival status, right? And notice that survived is a true false, and we see these as the row labels here at the left, right? So the leftmost here gives you the row labels. How about H histograms grouped by class? So I want it to be grouped by class, which is why the class entries are the row labels. Now, we don't have any columns here. We can go further, right? We can go further to the left. Reminder, we are using right to left. That's important. Not in the above diagram, we group by class, which was in rows. And now we go further. We put sex at the leftmost column. And now class is in columns because class is the second argument. So if we evaluate this, we get instantly nice histograms that are grouped by sex and class. And the column labels are class. That was the second argument here. The row labels are the first argument, that is sex. Let's look at what the survival situation by sex looks like. And you can see that the females have survived, and there's more females that have survived than males. And my next point, we talked about function composition during the first session. You remember that this is left to right, and this is right to left. And mind you, function composition is the construction of functions when not applied to data yet, right? You first construct the function and then comes the data. So keeping in line with right to left model, we want to compute the survival ratio per sex, grouped by class and sex. So we want to start with survived at the very right. That should give us a one-dimensional list. You can think of this as rows and column. It's a one-dimensional list. We want to get true, false, so we apply bool. Bool returns 0, 1 for false and true. So next, then we compute the mean, and then we want a we want a real. We want class grouping and then sex grouping. So this is how we go right to left. Survived, turn it into 0, 1, compute the mean, give me a real, then group by columns and class, and group by rows and sex. Totally right to left. You saw how I went there. So if we evaluate this, then we get this table, right? So these are the averages computed with this. Our initial data was survived, which was true, false, but we've converted it to numeric data with bool, and columns are class, rows are sex. So if you were on the Titanic in 1912, you better have been a woman. We can also change the grouping order. We can group by sex first and then put class into rows simply by swapping that, right? This is the same thing until right to left until we come to the first two columns. So now the row labels are class and the column labels are sex. Overall, most people died, right? Only 38% survived. And we can also list plot the survival situation, the survival status by age. And when you look at this, you will see that most people who survived were either at lower ages or at higher ages, and most people died in the middle ages. All right, and you can also define your own function to outsource longer expressions. So when you think, for example, that this is too long, then write your own function for this. I called it getMean. And where you use this long expression, just say getMean, right? You get the same results. Here's the table, here's the plot, by using your function getMean. And again, this is just a function composition. There's no data in it yet, just a function. All right, I'm looking at the time. It's now 40 minutes past. I wanted to do more with the Deutsche Börse data, and I wanted to see if there's any questions. If there's a lot of questions, I should probably break up now into the Deutsche Börse data later. If there's not a lot of questions, I think I will just go on. I still have
we have 20. One question from one user.
All right, let me look at it. Yeah, this I have to prepare, and I will prepare. I will show you next session, right? Interleave data form as JSON and PCXs. I will have to research that, right? I don't know what PCXs is. I use a lot of JSON. Statistical offices use them. I will prepare that for next time. All right, as that's the only question, and I still have 20 minutes, I will proceed. So I used the Deutsche Börse data last time, and I now would like to give you some comparisons between handling raw data and analyzing the raw data versus doing it as a data set. So I import the data. The last data available was for April the 30th, because Labor Day was a holiday in Germany. So I don't have the data for yesterday. We have to take the data from 2 days ago. And remember the column headings. And I'm now turning this into a data set, and I then can start querying that. So for example, the symbols, these are the symbols in the order in which they are in the data set. Keep in mind the data set is ordered. So IUSM was the first one that traded, all right? And we have 26 of those here. So these are the symbols that we have. And again, look how easy it is to scroll through that page-wise or go to the last one. Imagine you had to scroll the entire screen. I like it so much better when they have this table structure in the front end, and then I can go with it. And if you look very closely here, you may see that the slider bar has the up and down arrows. So given that this is almost 2,600 elements, I can simply slide here, right? See how convenient that is. You probably can't see that widget under the double arrow, but trust me, it's there. So very nice scrolling, right? It leaves your overall window intact because you scroll inside of something rather than scroll the whole window. So let's sort these by first column, and you can use the function key sort for that. And again, keep in mind, this is right to left. So we start with the symbol. We want to have the counts per symbol, and then we want them sorted by the keys. And 540 may not look like a symbol, but it is, right? In the ASCII code, first come the numbers, then the uppercase letters, and then the lowercase letters. You will see that these are symbols. Here you see some uppercase characters in it. And then the last one is ZSRI in the symbol at the Eurex. All right, very convenient. And I'll now show you a couple of equivalent ways to do this. Pick whatever you like best. I prefer the one above, not the following three, but based on how you think about this, right to left, left to right, operator notation, composition, or right composition, you can use different ways to do that. Right here we use the key sort as the last one, but this is prefix because we're giving it as an argument to the data set. We can put these two together in the last one, right? That makes the data set expression simpler, but you still have to specify them. And then we have counts and then to key sort, right? So this is right composition as an argument. How many are different symbols, right? We can query for, we want the union of all the symbols and then just take the length. So union guarantees us that every symbol is unique. It occurs only once. I ask for the length of it, right to left, I get these 2,600. I can also go to the raw data, right? Take the second column and do the same, right? Take the second column, pick only the unique elements, ask for the length. So you may find one or the other easier to use. Sort by the symbol counts. I can also do that. And well, now I start with 1, right? And then the last ones should be the highest. So there were 508 for the last, for IFX. That's the symbol with the largest number of entries in that file. Show the security descriptions that have Kommanditgesellschaft auf Aktien, KGaA in the name. So this is an example that we had also last week, but this time notice that this is a data set. We have this grid around and it's the same data, but here it's in a list, right? This is what I showed you last week. And we can also use the data set for that. We start with the security description, then we take the union. Note that this is right to left, right? So first comes the union and then comes the select, and select itself. It is itself an operator notation. All right, same as a list. What currencies and how many entries per currencies? Well, we have 5 currencies, and with counts, I also get how many entries there were in that. So almost 71,000 traded in euro. Not a lot in US dollar, and so forth. Here the Swiss, the krone, I think that is the Swedish krona, not a lot. And when I use counts on the raw data, I get it back as an association, right? I've also shown this last week. Very convenient to see, right? The key shows you the currency and the value is the number of entries in the underlying data. What security types and how many entries per security type? Well, let's look at them. And again, I like both of these types of query. Give me a data set, then I get it as a table back. and give me an association. Total traded volume for the day, right? So we can ask for total inside the data set, or we can take the second last column, total it up, or we can do it with a pattern matcher to extract the second column, total it up. Total number of trades for the day. Again, these three formats, pick whatever you like best. And notice how code efficient this is. Just a few keystrokes, and you get your solution very quickly. Just a few keystrokes, and I'll show you three options. Show them together, right? You can also show them together in a data set or in a list. The average number of instruments per trade. That's a little bit trickier, but it shouldn't be too much, right? To get the average number of instruments per trade, we need the total volume, the traded volume, and we need the number of trades. And then we divide that into the number of trades. So we can do it in a database with this query. Just take the first argument, divide by the second, or you can use left to right in this one, where you total first, then you make a division, and then you go to n. Or you can use cases in order to extract the second last columns, and then you compute this one total divided by the other total, whichever you like best. Certainly, here I think the data set solutions are simpler and shorter, but not always, right? So max price for the day, that is now the fifth last column, or we just query for the max price. That was that fifth last column, and we ask for the max. So this is the max price of anything that traded during the day, two days ago. Give me the min price for the day. So this is in the fourth last column, right? Notice that this is the fourth one here, the fourth one here, and ask for the minimum price, and that was the minimum price that traded for something. Volume per symbol sorted by symbol. So here we have the volume sorted by symbol. And the key sort has to be applied last, right? So that's why I use group by, and then I use right composition. Lufthansa volume for the day. And show in help browser. Yes, okay, so this uses the signature here on an association, right? Select from this association where a number is larger than 2, right? So you have this pure function-like syntax in the select, and that's what I'm using here in the select. And the way you do that is that you put the column label directly next to the hash, right? This says, I want the column that gives me the symbol. That's what I'm selecting. So I start with traded volume, right to left, and then I'm selecting by column Lufthansa. And the same here. Or when you don't care about the fact that you pick a particular column and you can get it directly from that and want to use the raw data and not the data set, then you can just go to the raw data.
Andreas, since you're comparing the raw data and data set, can you comment which one you prefer for reading? Like, if you want to read the code based off data set, is it more readable?
I think that totally depends on the person, right? I think that's very subjective. If you work for a corporation, there usually are programming standards, at least there should be. And maybe a programming standard will determine that. Maybe the group's policy says that, or your boss says that. I think, I use all of these. My recommendation would be pick whatever you think is best. There are benefits in using directly the raw data if you're only interested in one number, and that's the case here. But there are big benefits when you want to look at a lot of data, analyze it, compare it, browse it, and scroll through it, and then I would use the dataset, right? The dataset is there for interactivity. That's the main reason or the main kicker.
Excellent.
And if you don't need so much interactivity, and you understand your data, you know exactly how this is structured, and you don't need the activity, then, well, by all means, go directly to the data, right? It kind of depends on the purpose. If you're presenting to a group or an audience, then maybe the data set is better because it's more interactive. If you just want simple answers, I sometimes just go straight to the raw data. All Lufthansa entries. So this is now the entire Lufthansa activity to get 2 days ago. And again, keep in mind how nice this is to scroll, right? Maybe you see it in the right columns that I'm actually scrolling at. You don't see it in the left columns, but the right columns tell you that I'm scrolling through all these 473 entries. Yeah, right? It's 473 entries. I can jump to the end. So that was probably close for the day. And I can jump to the beginning. I can scroll page-wise, right? Here, these arrows. And I can use the slider, just very convenient. So if this is what you want to do, then use the dataset. Lufthansa min price per 1 minute bucket, right? So here I need to extract 2 columns now, and you do that by using a list, in parentheses, at the rightmost, right to left. So I need to extract time and min price. And I don't even need to further process it or do anything computation because I'm just querying on the Lufthansa column. So there is nothing more to be done to the right of the select, right? You get them now, and again, scroll through it. You see the time, column changing, and the price. All right, Lufthansa min price day plot. So this is the minimum price of Lufthansa for the day, right? Very easy and convenient. But since this is about the session is about the data set, I'm showing you the data set here. We looked at this last week with the cases. So I want to speak out a caveat at the end of my session. The data set has the potential to cause infinite computations when wrongly used. Because you are pre-constructing a query, a function composition, and then you're applying it to data. So you can make a lot of mistakes with that. And my suggestion is you try with small data first, you get experience with query functions, and then carefully scale into the full size of your data. That way you're not hanging the system, you're not crashing the kernel. That way, start small and grow into it, right? Software technology these years is all about scalability. Everything is about scalability. But it's also a very prudent approach for you to get into this. If you start big, the whole thing may just crash on you, and you don't know, is this going to finish in 3 minutes, 3 hours, 3 days, or 3 decades? So scale into it. Start small and grow into it. All right, that's the end of my session for today. What I want to show you now is the homework that I have for you. I have also a point that I would like to address. Sometimes the job of a data scientist is to also find out if there's something wrong with the data. Sometimes your job is not to create beautiful things from the data that you were given, but a good data scientist also finds out what's wrong with it. Can I trust this data? Are there any conflicts? Are there any anomalies? So I briefly want to talk about the data quality items. You need reliable data to begin with, and there are many dimensions in which your data can be bad. Right? The entries themselves can be wrong. The data can be incomplete. I make a distinction between wrong data and incomplete data. I think incomplete data should not be called wrong. The data itself can be outdated. The data entries can be partially correct and partially wrong. The data can be malformatted. You have to take care of that when you're reading in the data. And it can be inconsistent. And for example, one thing in finance can be some data is discounted by interest rate and some is not. So you may have inconsistencies in your data where you don't know where they're coming from. Or you could have actual for some entries and averages for other entries. Strictly speaking, all the data that you take should come with what's called a data specification, but usually you won't get that. But keep that in mind. That is some of the problems that you may run into. So you have 2 choices: get better data or restrict your analysis to those parts in the data that are reliable. You don't have to throw away all the data if you can't get better data. You can restrict your analysis to those parts that you deem reliable. So for this homework session, I use such data. It is partially wrong. So this is the county level data for the presidential election in November 2016. So we'll make queries on the county level data, and I will provide a CSV file with all these aggregations. This is the best data. This is the best county level data that I was able to find. And if you know of a better source, let me know. But there are problems with this data. The largest problem with this data is that every state conducts their elections on their own. And it's very hard to collect that. You have to go state by state by state to collect this, because the way the election laws are written is every state does it on their own. So we needed a compilation enthusiast who compiled all this data. So this data has at least two problems that I'm aware of. The vote totals for Alaska are wrong, and there are not enough Clinton votes for California. So for this homework, we'll exclude all Alaska data for the detail and all vote totals. We'll only look at the county level voting results. I wasn't able to find any inconsistencies here. And at the end, you have to try to find out what's wrong with the Alaska numbers. That's part of the homework. Tell me what's wrong with the Alaska numbers. Keep in mind, sometimes the job of a data scientist is not just to deal with data that works, but also trying to find out what's wrong. So you have to import the CSV file, look at the column headers so you know what they are, and then answer the following questions. And as an exercise, you should try to handle the data both as a raw two-dimensional table and as a data set. All right, so here you import the data. And for this spreadsheet, I have written solutions that I think make sense, but I have hidden the input cells, right? So you will have to go here and then I hide them. That way you have the solutions to double check, but please try them first. So I'm not showing them to you immediately. Try it first and then compare with the input cells that I have hidden for you. So it's questions like how many counties went Dem or GOP? Which counties went Dem in Illinois? Which counties went GOP in New Jersey? Were there any counties in Vermont that went GOP? And so on, right? I have a couple of questions for you. And at the very end, I couldn't resist playing with the new and 12 find anomalies function at this point. And as an extension to this homework, let's use the out-of-the-box function find anomalies if we can glean some interesting insights. And I discovered that it provides us already with a big city detector when standard parameters are used, because the cities vote different from the rural areas. And to my surprise, when I use find anomalies on this data without any parameters, no target function, no trimming, just straight out of the box, it already threw 5, 6, or 7 anomalies. And those are the big cities. And I make a comparison of that with that. And we find the big cities here are detected by find anomalies. So you also have to take it with a grain of salt. All right, well, you see that. I'll explain it. I'm coming to the session end. It's now exactly 6 p.m. I think I've landed on the spot on the minute.
We also have one more question.
Yes.
I wonder if you could address that.
Can you use dynamic to see items added into a data set for real-time entry? Good idea. I will prepare it for next session.
Okay, excellent. Thanks, Andreas. I would like to remind everyone that Andreas has provided a community post. You can go there, you can see the lecture notes, homework, and you can ask any question that you may have. Thanks again, everyone. See you next time.
Great. Thank you. Bye-bye.